Let's solve an example for the range of a projectile, or in other words, for how far a projectile can go in the horizontal direction. We have a person that kicks a ball from the ground with an initial speed of 15 meters per second at an angle of 35 degrees. The question will be, how far does the ball go before it falls back on the ground? So just as in the other projectile motion examples, we will be using this set of 4 equations. One that pertains to the motion along the horizontal direction, that's equation 4 here, and 3 for the vertical motion. Let's look at the problem here. I will draw the picture on a y-axis graph here, and I will look at the trajectory of the projectile motion. We start here at the ground, and we know that it's going to go up and down while simultaneously drift to the right. In the vertical direction, we'll see gradual slowing down and then speeding up on its way back, while in the horizontal direction, the motion will be with a constant pace. The ball is kicked with an initial speed of 15 meters per second. So I'm going to draw here a vector here with a magnitude of 15 meters per second. But that vector is at an angle of 35 degrees with the horizontal. So it's kind of easier to just pull that vector out of that picture and look at the vector itself alone. So here's the vector for the initial velocity, 15 meters per second at an angle of theta that is 35 degrees. And I need to find out what is that motion equivalent in terms of moving along the x direction and along the y. To that end, I'm going to draw a perpendicular from the tip of the vector for the initial velocity down to the axis for the horizontal direction, and that will be the horizontal component of the initial velocity at that initial moment, Vx naught. We see here we have a right triangle, and in that right triangle, Vx naught is actually the adjacent side to the angle theta. So from trigonometry then, I know that this is going to be equal to V naught cosine of theta, or 35. Numerically, that will be 12.2873. If you decide to solve the problem numerically, I would advise you to keep extra digits. Remember, this is very early in the solution of the problem, and we do not wish to accumulate round-off errors. For the y component, that will be the opposite side, the side opposing the angle theta. So then I know that the y component of the initial velocity will be V naught sine of 35, or theta. Numerically, that will be 8.604 meters per second. So what is the question? Usually by this time, sometimes I even forget what the question is. I go back to the problem. Let's finish the reading through the problem. The question was here, how far does the ball go before it falls back on the ground? So we have delta x equal to what is our question. Before I go and look for the solution, let me just mention one more very important detail here. The ball goes back on the ground where it started. In other words, the final position along the y has to be equal to the initial position along the y. With that, let's see if we can figure out the solution, how to go about the solution of this problem. If the question is about how far a projectile goes along the horizontal direction, there's only one equation that actually relates to the horizontal motion, and that's equation 4. X is equal to x naught plus Vx naught t. If I rearrange it slightly and I move x naught to the left, the difference between the final and the initial position along the x will be that question in the problem, delta x. And so if I want to find delta x, I will just need to put the value for the initial velocity along the x, which I know it's going to be V naught cosine of 35, or in the lower left corner of my screen, I even put the numeric value of 12.2873 meters per second. And then I'll have to multiply by the time. So the question very quickly becomes, how much is the time? So how do we find the time? This is when we actually look at the equations for the motion along the y direction. Once again, we're going to use the second equation here, which relates to the position. So equation 2 in this case will give us the vertical position y will be equal to the initial vertical position plus v y naught t minus 1/2 gt squared. Once again, I'll move y naught to the left-hand side so I can see that delta y, which in this problem is 0. Remember, the final and the initial vertical positions are equal to each other, so that will give me 0 on the left-hand side of this equation, will be equal to the initial velocity along the y direction multiplied by the time. That's the vy naught t term, minus 1/2 gt squared. I know what the initial velocity along the y is. That's why I did that little analysis in the lower left corner of my screen. So if I replace vy naught with the v naught sine theta, or you're welcome here to put the numeric value if you wish, 8.604 meters per second, the equation then becomes 0 is equal to v naught sine theta times t minus 1/2 gt squared. Here I can cancel 1 power of t, or mathematically speaking, I can divide every single term in my equation by t, and that's how I'm going to cancel the t. There's some, usually we have to watch out when we divide by something, because in mathematics we have to make sure that that value can never be 0, otherwise we'll end up in trouble. This is a question about physics and specifically about a projectile motion, so common sense tells us that it doesn't make any physical sense that the time could ever be 0. We know it's going to have it's going to take some non-zero time for the projectile or for the ball to go all the way up and down. So here we don't have to worry about accidentally dividing by 0, just cancel the t, and I will move the second term to the left, that 1/2 gt squared, which will be 1/2 gt now. So my equation becomes 1/2 gt has to be equal to v naught sine theta. Remember, I just canceled out the t. And with that, I have an expression for the time of flight of that projectile. The time it takes will be equal to 2 times the original velocity, the magnitude v naught, sine theta divided by g. G is the gravitational acceleration, 9.8. With that, I can go back actually to the equation 4. Remember, I got stuck there in my solution for the range or for the distance of the projectile. So I'll have the distance along the horizontal will be equal to Vx naught multiplied by the time of flight. And I already know that the time of flight, I actually have an expression for it. And it turns out that the time is 2v naught over g times sine of theta. Not only that, but I also know what the initial velocity along x is, again, from that trigonometric analysis in the lower left corner. So I'm going to replace Vx naught with its expression V naught cosine 35, so that for the distance of the ball, I will have to be equal to V naught cosine theta, that's the x component, times the expression in the brackets, which is the value for the time of flight, 2 times V naught over g times sine theta. Let's make some room here. I need a little bit more space. Here you can actually start plugging the numeric values into the expression for the range or for the distance. I personally prefer to wait just a few more steps. I like keeping symbols for as long as possible. That avoids the issue of round off errors. And also sometimes keeping symbols can actually show you patterns in some expressions. So let's see what happens if we keep the symbols just for a few more steps. What I'm going to do first is to combine the V naught and V naught. It appears twice in my expression. So I'm going to have 2 times V naught squared divided by g. And then I'll switch the order, so I'll have sine theta times cosine theta. Even more, I'm going to combine the 2 and sine theta with cosine theta and recognize the trigonometric formula for the sine of 2 theta. So I can actually write that the distance that the ball will reach in the horizontal direction will be equal to V naught squared divided by g times sine of 2 theta. This is called the range of a projectile, and some textbooks and many students elect to treat this result as a formula. I personally prefer not to, but there is no law. It's totally up to you how you're going to go about it. If you decide to treat this as a formula, you can put it on your formula sheet depending on your professor. Keep in mind that this formula is applicable only when the final and initial vertical positions are the same. Remember, we said that the final position y had to be equal to the initial position y naught. If for some reason the ball ends higher than its original position or lower, then you just have to go back and repeat all the steps in this video. The physics is the same, the analysis is the same. The only thing different here will be the math. You'll just end up with some quadratic equation. So the algebra is going to be just a tad bit more complicated than what it is now, but otherwise the physical solution is the same. So with that, let's finally put the numeric values here. For V naught, it was 15 meters per second. The angle was 35 degrees. And so for the range of the ball, I find out that it's equal to 21.6 meters. Final comment here. There is a maximum distance that this ball can reach. It's called maximum range. And look at the formula for the maximum range. It depends on sine 2 theta, and we know the sine function is a limited function. Its maximum value is 1. So that happens when the angle is 45 degrees, and for which the range turns out to be equal to V naught squared over G. So if you are tossing a ball or kicking a ball and you want that ball to reach the farthest possible, your best angle, you need to aim at for an angle that is 45 degrees or approximately 45 degrees to reach the maximum possible distance.